Welcome back, guys. We're going to talk about the next type of graph that we can draw, which is going to be a velocity time graph. And a velocity time graph is going to display how velocity changes. When you have a change of velocity, that's known as acceleration. And our average acceleration is going to be the change in velocity versus the time elapsed. So in this case, there's a picture of a car. It might be hard for you guys to see, but it's starting at rest. It has a velocity of 0 meters per second. And its acceleration is 15 kilometers per hour per second. So this tells me how much it's going to change every second. So 1 second later, its velocity has changed by 15 kilometers per hour. Now its velocity is 15 kilometers per hour. At t equals 2 seconds, so 1 second later, its velocity will have changed by an additional 15 kilometers per hour. So now it's at 30 kilometers per hour. And in the final picture, they go from 2 seconds to 5 seconds. So now it has changed by 15 kilometers per hour 5 times. And so now it would be 5 times 15 kilometers per hour. And that's going to be 75 kilometers per hour. It's important to note that the acceleration doesn't tell you how something's traveling. It tells you how it's going to change in the future. So knowing something's acceleration, you don't know how fast it's moving. It could be positive or negative. If you remember, when we decide what's positive and negative, we take things going to the right and up to be positive, and things going to the left and down to be negative. So in this picture, this car is going at 15 meters per second to the right. This is a positive velocity. This acceleration is directed to the left. You look at the direction of that arrow, so that's going to be a negative acceleration. So since the acceleration is opposing the velocity, it's going to cause that velocity to decrease. How much is it going to decrease? Well, they're saying that it's going to happen for 5 seconds. So for 5 seconds, it's going to decrease by 2 meters per second every second. And so you're going to have 5 times -2. So it's going to decrease by 10 meters per second. So whereas it was going at 15, it has lost 10, it's down to 5. Negative acceleration is not the same as deceleration. Deceleration is going to be something that is slowing. And that's going to be when the velocity is in the opposite direction as the acceleration. Negative acceleration is going to mean that the acceleration is directed in a negative direction, which could be backwards, down, or to the left. So in the case here, this object is slowing down, but it has positive acceleration. If you were to drop a rock, the rock would speed up, but it would have negative acceleration because gravity is directed down. So the formula for this acceleration is the change in velocity over time. In our MKS units, meters, kilograms, and seconds, the unit for this would be meters per second over seconds, or meters per second squared. You can also have how the acceleration changes, which is meters per second cubed. That is known as the jerk. Or how the jerk changes, which is meters per second to the 4th power, which is jounce. You could also have how the jounce changes, and that is meters per second to the 5th, which is snap. Meters per second to the 6th is crackle. Meters per second to the 7th is pop. And I'm serious. We're almost always going to deal with constant acceleration. If you don't have constant acceleration, it requires calculus to solve the problems. So our equations will have constant acceleration. So that'll be an assumption for almost all of our problems. All right, so we're going to graph velocity versus time. Again, the first thing listed is your y-axis. The second thing listed is your x-axis. On a velocity time graph, the slope will give you the acceleration. That could be positive or negative. And the area under the curve will tell you how far you've gone. By unit analysis, we can see this because our slope is going to have the units of meters per second over seconds, which gives us the units of acceleration. The area under the curve, distance traveled, is going to be some area. So we would have meters per second times seconds, and that gives us the unit of meters, which is what we measure distance and displacement in. All right, a car accelerates from 0 meters per second to 20 meters per second in 10 seconds. It then remains at 20 meters per second for 20 seconds and stops in 30 seconds. Graph velocity versus time, find acceleration for each time segment, find the distance traveled, and graph the position versus time. So that's a lot of steps. All right, so they give it to us to start with what our increments are, so we don't have to pick that. In our first increment, it takes 10 seconds to get to 20 meters per second. So again, if we do our x as time and our y as velocity, I'm going to have 0, 0. At 10 seconds, I'm going to be at 20 meters per second. Then I'm going to stay at 20 meters per second for 20 seconds. So I'm going to add 20 seconds to 10, which is going to take me to 30. And this is going to still be at 20. And then I'm going to stop in 30 seconds. So I'm going to add an extra 30 seconds, which will take me to 60, and that'll be 0. Because stopping is represented by 0. All right, so I'm going to start at 0, 0. I'm not moving. And we're saying that in the first 10 seconds, I'm going to go up to 20 meters per second. So I'm going to go 10, comma 20. Scroll this up a little bit so I get 20, 10, comma 20. I'm going to connect this with a straight line, or try to the best I can based on the smart. So this tells me how the velocity is changing, and this should be a straight line. The slope should be what this constant acceleration is. Let's calculate that. So my slope, if you remember, is y2 minus y1 over x2 minus x1. So in this case, it's going to be 20 minus 0 meters per second over 10 minus 0 seconds. And so that tells me that everywhere on this line, it's 2 meters per second squared. What else can I tell from this segment? I can find out what the displacement is, or the distance. This is going to be the area. So if I make this into a shape, this line should be over just a little bit. Sorry about that, guys. I was past 10 seconds. This should be a shape that you would recognize as a triangle. The area of a triangle would be 1/2 base times height. So I'm going to have 1/2, 10 seconds, times 20 meters per second. So that means that in this segment, I traveled 100 meters. In the next segment, I stayed at the same speed for 20 seconds. So my next ordered pair was 30, comma 20. The slope of this, a straight line, is 0. So if the speed is the same everywhere, you have no acceleration. But I can find out how far I traveled by looking at this big rectangle. And this big rectangle, if I do the base times the height, would have a base of 20 seconds and a height of 20 meters per second. So that means that I traveled 400 meters. In the last increment, I return back to my starting point, which is a speed of 0. I should say my starting speed, which is a speed of 0, and this would be at 60, 0. And so to find my slope, I would take y2, which is 0 meters per second, minus y1, which is 20 meters per second, and then subtract 60 from 30 seconds. And so my acceleration is negative 2/3 meters per second. Every second, my velocity decreases by negative 2/3. And finally, how far did I go? That's going to be this big triangle here. And so that would be just 1/2 base times height. So this is going to be 1/2 30 seconds times 20 meters per second, which is going to be 300 meters. So how far did I go in the entire time? I went 100 meters, and then I went 400 meters, and then I went 300 meters, for a total of 800 meters. All right, when we get back, I'm going to show you how to make this graph into a distance time graph and how to equate distance time graphs to velocity time graphs.